Experiment of the Wheatstone bridge. The objective of this experiment using Wheatstone bridge to determine an unknown resistance. Apparatus, Wheatstone bridge, power supply, galvanometer, switch, resistance box, connecting wires, and resistor of unknown resistance. Theory: Wheatstone bridge is considered to be one of the accurate electric circuits used to determine the value of an unknown resistance Rx by comparison with the three known resistors R1, R2, and Rs. The bridge in its simplest form consists of four resistors, a power supply, and sensitive current detector called galvanometer. These components are connected as shown in figure below. For the slide wire bridge of figure, the AC represents the bridge wire. R represents the standard resistance of resistance box. X represents the unknown resistance. And P represents the sliding contact point that slides along the wire AC. When the bridge is balanced, the sliding contact divides the wire into two different lengths, segments L and 100 minus L. The resistance R is equal to the resistance of wire L, and the resistance X is equal to that of the wire length 100 minus L.
What is the problem in the experiment of Ohm's law? In Ohm's law, we have a power supply and we have a resistance. We connect an ammeter to measure the current in the circuit. Then we connect a voltmeter from both sides of the resistance to measure both values of V and I. Then by dividing the voltage over the current, we calculate the value of the resistance R. Now imagine that this resistance has a value of 10 ohms and that the current measured by the ammeter is 5 amperes. Now in this case, these 5 amperes are going to pass through this resistance, and the potential difference can be calculated by Ohm's law, V equals I times R. So the potential difference around this resistance must be 50 volts, 5 times 10. But what happens is the following. When we connect the voltmeter in order to measure these 50 volts around this resistance, now this current, the 5 amperes, when it reaches this point, in fact does not go entirely to the resistance. Part of the current will go to the resistance and another part will go through the voltmeter, since there are two paths possible for the current. But this voltmeter is always made such that its resistance is very high in order to reduce the value of the current that passes through the voltmeter. But regardless how small is this current, still there's a current that passes through this resistance. Imagine that, for example, 4.8 amperes will pass through the resistance and only 0.2 amperes pass through the voltmeter, only 0.2. This will make the potential around this resistance 48 instead of 50. So the reading of this voltmeter is going to be 48, not 50, which is V times R. 4.8 times 10 is 48. So the ammeter will measure a current of 5, while the voltmeter will measure a voltage of 48 volts. And when we use these two values to calculate the unknown resistance R, we will have 48 over 5, which is in fact 9.6 ohms. So we will measure a 9.6 ohms while the actual value of the resistance is 10, not 9.6. It is 0.4 less than the actual value, and this error is caused because of this small current that goes through the voltmeter. So it will be fantastic if we can measure the voltage without having a current passing through the voltmeter. And this is the rule of Wheatstone bridge. It measures the value of the unknown resistance without any current passing through the voltmeter. So what is the Wheatstone bridge? Let's see. Now, the idea of the Wheatstone bridge is the following. We use 4 resistors connected like this. One of these 4 resistances are something unknown. Let's say this one, we call it Rx, an unknown resistance. This one is called Rs, this one is called R1, this one is called R2. And we connect the power supply here to supply the current. Now the current generated by the battery, and when this current reaches this point, I will call it point A. So at this point, the current will be split into 2 parts. Part goes up, I will call it I1, and another part goes down, I will call it I2. Okay, now we connect a voltmeter or a galvanometer. The galvanometer is the main part of the voltmeter. So you can say simply this is a voltmeter between these 2 points, this point and this point. I will call them point B and point C, and this point I will call point D. Now, if assume that the galvanometer reading is 0, and after a few minutes I will tell you how can I make this reading of the galvanometer 0. If you assume that this reading is 0, this means point B and point C are at the same potential. There's no potential difference between B and C. So they have the same potential since the difference is 0. And this means that no current will pass through this branch. No current will pass through the galvanometer since the potential difference around the 2 ends is 0. So the current I1 after passing through the resistance Rx will pass entirely through Rs. So this is I1 itself. So I1 will pass completely through Rs. No part will go through the galvanometer. The same thing can be said about I2. I2 after passing this resistance R1 at point C, no part will go through the galvanometer. The entire current will go through the resistance R2. So the current here is also I2. Now, since the current in Rx is I1 and the current in R1 is I2, so the potential difference around this resistance is I1 times Rx according to Ohm's law, and the potential difference around R1 is I2 times R1 according to Ohm's law. But these 2 potential differences are the same, since we said from the beginning that point B and point C are at the same potential. So the difference between A and B is the same as the difference between A and C. So potential difference between A to B is the same as the potential difference between A to C, since B and C are equal. But this potential difference from A to B is I1 multiplied by Rx, and the potential difference from A to C is I2 multiplied by R1. Now if we go to the other side, we can say the same. Now the potential difference between D and B is the same as the potential difference between D and C. So VBD equal VCD. But this potential BD is I1 multiplied by RS, and the potential CD equals I2 multiplied by R2. This is equation number 1, and this is equation number 2. Now if I divide equation 1 over equation number 2, I will get the following: I1 Rx, this one, divided by this one, which is I1 Rs, equals I2 R1 divided by I2 R2, from which we can cancel I1 from this side and I2 from this side. We come to the formula that Rx over Rs equals R1 over R2. Now from this formula, if I know the values of the three resistances R1, R2, Rs, these three, I can calculate Rx, which is a precise measurement without any current passing through the galvanometer. And this formula, in fact, can be written in a different way, which is more easy to be memorized. We can here multiply cross multiplication like this. So we can say that Rx multiplied by R2 equals Rs multiplied by R1. This formula is very easy to be memorized since it represents the cross multiplication in the circuit here. Multiplying Rs by R1 equals multiplying Rx by R2, like a cross multiplication. But all these things are true only if the reading of the galvanometer is 0 and no current is passing through this branch. So the next step, I will explain how can we make this current 0 and how can we make the reading of the galvanometer 0. Okay, so what we do in order to make the reading with the galvanometer 0 is the following. These are the two resistors Rx and Rs. And here, these two resistors, which were called R1 and R2, we replace them by a wire which is 1 meter long. A 1 meter long wire, yes, 100 centimeters. And we connect, of course, the power supply here at the two ends. Then we use the galvanometer connected to this side, and here we have a pointer. So we touch the wire, but we can move left or right until we find the location where the galvanometer reads 0. Because when I connect the galvanometer to this point, this means this part of the wire, this part, represents the resistance R1 in the previous circuit, and this part represents the resistance R2. So when I move this pointer, for example, towards the left here to this point, this will make the length of R1 smaller, shorter, which means the value of R1 becomes less, since the resistance, as we know from the last experiment, depends on the length. Resistance equals the resistivity times length over area. So when we make the length shorter of the resistance R1, the value of R1 becomes less, while R2 becomes longer and its value becomes larger. So by moving this pointer left or right, we are in fact changing the values of R1, R2 until we come to the location for which the reading of the galvanometer is 0. So now our relation is Rx R2 like this multiplied equals Rs R1 multiplied. But since R2 and R1 are a wire, we can replace its value by this. So we can say here Rx is multiplied by R2, which is rho L2 over A, and by L2 I mean this length, the length of R2, and for this side rho L1 over A. Notice that I used L1, L2, but I didn't use A1, A2, since the area of or the thickness of the wire for this part or this part, the thickness is the same, and this wire is of the same material, so no need to say rho 1, rho 2. Resistivity is the same for both sides, area is the same for both sides, but the length of the right side is different than the length of the left side. So I can cancel out this resistivity and this area, and I come out with the relation Rx L2 equals Rs L1. So it's the same relation as before, but we replace the resistances by the length. So multiplying Rx by L2 equals multiplying Rs by L1, and here we can control the length by moving this pointer left or right to find the 0 point. So this is the theoretical part of this experiment, and this is the idea. Now we go to the lab and do the experiment. This is the setup we are going to use, as you can see. So we start with this meter stick and the wire connected here between the two ends, from this end to this end. It's 1 meter long, and from both sides connected to the power supply. This side is connected to the positive terminal, and from the other side it is connected to the negative terminal. Now this is the location where we will connect the unknown resistance Rx. So I will bring Rx now. This is Rx, the unknown resistance. Its value is hidden here, and I will connect this resistance between these two sides. Okay, Rx is now connected in its place. Now in this location we need to connect the known resistance Rs, and I will start with a resistance of value 50 ohms. This one, connect this 50 ohms to these two sides. Okay, now the circuit is closed, and we need just to connect the galvanometer. Okay, the next value for Rs is 100 ohm. It is connected now, and I will move the pointer until I find the 0 location. You see the needle is moving. Okay, so this is the 0 location. Here we go to the other side, and here we go to this side, and the 0 takes place exactly here, which is 53 centimeters. So the distance to the right is 53, the distance to the left is 47 centimeters. Now I will go to the next value of the Rs, the known resistance. So now the third value for Rs, I am using two resistors, 150 ohms connected in series, and this represents a value of 150 ohms. So the value of RS is 150 ohms. And now I will move the pointer on the wire to find the zero location. Not yet. Okay, now you can see I can move it left or right, and this is the zero location when the pointer is at exactly 64 centimeters. So the distance to the right is 64, the distance to the left is 36. Now, as a fourth reading, I'm using the same two resistors, the 50 and the 100, but I'm connecting the two resistors now in parallel. And when they are connected in parallel, according to the formula we know for the resistors connected in parallel, this represents a resistance of 33 ohms. So the resistance is now 33 ohms, and I will try to find the zero location. Okay, this is the zero, you see. Now I come to the zero. I can move it left or right until I stop exactly at the zero. 26 centimeters. So the distance to the right is 26. The distance to the left is 74 centimeters. And we will finish this experiment with these four readings, and I will fill this data in the table, and I will show you the table after this part. So as you can see, I filled now the data in the table, and I removed the values written here 20, 40, 50, 60, 80. Since we don't have these values, I use different values, the 33 ohms, 50, 100, 150, and I used only 4 readings, not 6. So I skipped the last 2 lines. These are the values for L1 and L2 corresponding to each value of the resistance we measured. So using the formula now, you need to calculate what is the value of Rx for each one of them. Then you are asked to calculate the average value here, the average value of Rx. Then you need to calculate the standard deviation. So you calculate the difference between each value and the average squared. Then you calculate the mean of these 4 values under square root. This is called the standard deviation. So this delta Rx is in fact means you calculate Rx minus the average one by one. For each value, you subtract the average, then you square each value, which is this column, then you add them from n equals 1 to 4, because these are 4 values, then you divide by 4 to calculate the average. This is called in statistics the variance. Then if you take the square root, this will give you the standard deviation, which is the error in measuring the resistance. So that's it, and this is the end of this experiment.